right, working on Twitch. Is it working on YouTube? Maybe. Working? All right, I think we're also live on X, so let's get started. How's it going, Nuno? How's it going, Amelie? All right, so welcome to another Hoopo's stream. We're doing something a little bit different today. We're still in the space of AI and machine learning, but we're going to be in a different area than we're normally in. This is the biological and chemical space. We're going to be looking at two different papers that were recommended by one of our Discord channel members. This is one paper that's kind of chemistry flavored and then one paper that's biology flavored, but both papers are quite similar and they kind of use the same technique to get to the same place. So the first paper we're going to be looking at is paper released 29th January 2024 called Multimodal Molecule Structure Text Model for Text-Based Retrieval and Editing. So the multimodal part here is going to be basically, there's going to be two different modalities here. There's going to be text, and then there's going to be the kind of like structure modality. First things first, right? This is obviously not a machine learning paper, right? So one of the first things I noticed here is that here's a kind of standard machine learning paper. This is basically the clip paper. And here, obviously, you notice the two-column format. So that's kind of the first hint there. These papers do not have the two-column format. These are one kind of like single-column format. So that gives you the first one. And the other thing that I saw that was kind of weird here is, so in most machine learning papers, like pretty much the entire team will be affiliated with a single institution here, such as OpenAI in SF for this clip paper. But these papers are weird in that it seems like almost everyone has a different affiliation. Like look at the amount of institutions here. You have Arizona State University, HEC Montreal, Princeton University, California Institute of Technology, University of Illinois, Urbana-Champaign, NVIDIA Research, University of Montreal, Mila, Quebec. Like, what is going on here? Like I said, I'm not like a biology person, but how does this even work, right? If none of these people are affiliated with the same institution, are they even sitting in the same building? Is this how kind of biology research works, where you basically have a bunch of people that are all in a distributed way contributing to a single project? Because that's usually kind of difficult to do. So I don't know, just something interesting I noticed that is different from machine learning papers or standard machine learning papers is just the amount of institutions here. But going back to what these papers are about, both of these papers are basically, the easiest way to describe what they are is they're basically CLIP, right? Contrastive Language Image Pre-training, which is what is used in pretty much any kind of model that combines images and texts, right? They make use of these contrastively trained image and language multimodal kind of models, of which CLIP and all of its variants are the most popular. But basically, whereas in CLIP you are taking an image and then a bunch of text and then feeding the text through a text encoder, feeding the image through an image encoder, and then basically slowly training these text and image encoders such that you get an embedding space that is joint, right? And what that means, jointly trains an image encoder and text encoder. It basically allows you to use this embedding space to either look up an image given a text, look up a text given an image, find the similarity between a text and an image, right? So it's a very useful little embedding space. Both of these papers are basically going to be doing that, but instead of for images and text, they're going to be doing it for chemical structures and text, and then proteins and text. So these papers are so similar that I think actually the best way to do this is we're going to read both of them at the same time. So we're going to kind of be bouncing back between these. And it might be a little bit confusing, but I think it's actually the easiest way to do it because it's like reading them one after the other in like kind of a sequential order is just going to feel like we're doing it too slowly. How's it going, Majetti? So let's start with the abstract for the most recent paper here. There is an increased adoption of artificial intelligence in drug discovery. Drug discovery is just finding new drugs. Existing studies use machine learning to mainly utilize the chemical structures of molecules, but ignore the vast textual knowledge available in chemistry. Okay, so this is telling me that people have used AI/ML in chemical structure stuff, but this is, whenever they say chemical structure, they mean basically this, right? So like the actual little structure of a chemical like this, right? And there's two different ways of representing this. So they're going to mention this, but there's basically, you can describe things as what are called, let me see if I can find the exact thing here. So there's what's known as SMILES format. SMILES format is basically the chemical compound, but in this weird like kind of sequence of letters. So for example, this is what the actual molecule looks like, right? So you have, I'm not like a chemist at all, so I know, like, for example, this is oxygen, this is hydrogen, this is probably some kind of double bond, single bond. I think these might be carbons, but again, I don't actually know what I'm talking about there. But basically, there's two ways that you can represent that structure. You can represent it either in this SMILES format, which is basically turning it into text, and sometimes it's a little bit weird. So here, for example, I guess this is like the oxygen, right? But you're losing a little bit of information there, right? With this SMILES format, you're losing the kind of 3D nature. I think for a lot of these molecules, right, it's like those bonds don't just have, it's not just a graph with connections, it's also there's angles between them and there's distances, and it gets pretty complicated pretty quick. So I feel like this format is actually quite primitive to describe molecules. So that's one format. The other format they're going to be looking at is what they just kind of generically call a graph format. We'll get to it. I think it's somewhere over here. But yeah, here we go. So the SMILES string, that's the format we just looked at. And then a graph neural network, that's what GNN stands for, on the 2D molecular graph. Okay? So those are going to be the two primary formats for chemical structures. But it seems like most of the previous work, like they've largely just used databases of these chemical structures and kind of ignored the textual knowledge available in chemistry. Incorporating textual knowledge enables us to realize new drug design objectives, adapt text-based instructions, and predict complex biological activities, right? Here we present a new multimodal molecule structure text model called MoleculeSTM, which is the structure text model. That's what the STM stands for. By jointly learning molecules' chemical structures and textual descriptions via a contrastive learning strategy. So basically, there you go. It's going to be CLIP, but rather than images and descriptions of those images, it's going to be chemical structures and descriptions of those chemicals, right? So basically, the data set is going to be this. You're going to have some chemical structure either in this SMILES string format or in the form of a graph, right, where the graph is just going to be a bunch of nodes with edges. And then you're going to have basically chemical descriptions. So things like benzene is a colorless liquid with a sweet odor. It evaporates into the air very quickly and dissolves slightly in water. So you can see how now the way that they've formulated this problem, it's basically effectively CLIP. You basically have paired examples of images and text, and then you're going to use contrastive learning to train this shared embedding space, and that's exactly what they're going to be doing here. Okay. To train MoleculeSTM, we construct a large multimodal data set called PubChem-STM with over 280,000 chemical structure text pairs, which seems like a lot, but actually isn't. And this is one of the things that they kind of continually bring up, right, is that this is not a lot of data compared to what you see in the image and language domain. And even this data set is not even a full data set, so it's actually a subset of an existing data set. Yeah, here we go. We construct a structured text data set called PubChem-STM from PubChem, which contains the largest multimodal data set to date in the community. So PubChem-STM is their own curated subset of PubChem. And what the fuck is PubChem? PubChem is this. PubChem is basically like a giant database where I guess you can find, let's see if we can find benzene. There we go. Look at all these different types of benzenes, and you can click, and here you go. Here's benzene. Look at that. Flammable, hazard. Here's like a bunch of text. So this is really what they're leveraging, is this text information here, right? And that's kind of the whole MO with this paper, is that previous works kind of have ignored this vast textual knowledge. So they're like, hey, why don't we try to use that? Why don't we actually go into these databases here, of which PubChem is the best one, and then basically leverage the fact that we can create some kind of joint space that has all this text information mapped to the actual chemical structure of it. And maybe just a little bit more color here on what PubChem, here's the Wikipedia page on it. PubChem is a database of chemical molecules, and it comes from basically the United States National Institute of Health. More than 80 database vendors contributed to the growing PubChem database. So basically released in 2004. So it's just this giant government database of chemicals that has been contributed to by a huge amount of different companies. And you can see the actual URL is nih.gov. So this is a government database. Okay, but they have PubChem. That's way too big. So they create a curated subset, which they're going to call PubChem-STM. To demonstrate the effectiveness and utility of MoleculeSTM, we designed 2 challenging zero-shot tasks based on text instructions, including structure text retrieval. So structure text retrieval is, hey, given the structure, can you give me the text? And then text structure retrieval would be the opposite of that. Hey, here's this text. Can you find the structure for me? And then molecule editing, which is kind of like a crazy one, where you can basically, kind of like image inpainting, where you can take an image and then use some kind of stable diffusion to basically, given a little piece of text, draw something new inside of there. You can kind of do the same thing with molecules now, where you can basically say, actually there's a figure for this. So here's your input molecule, right? And then you add this prompt. This molecule is soluble in water. And then their molecule editing is then going to create a new molecule or edit the existing molecule such that it now has, I guess, this extra little nitrogen there. And that extra little nitrogen there makes it more soluble in water. Or this molecule is soluble in water and has low permeability. And you can see here how, in this case, the input molecule, whatever is here, gets replaced with that, right? So that's what molecule editing is. So down here, molecule editing. So what is structure text retrieval? Structure text retrieval is basically this. So in structure text retrieval, you're giving it the structure. So here we have different molecules, and then you're searching a database of basically text descriptions, and the text description will basically say, okay, this molecule is a combination of penicillins. Okay, like I said, I don't actually know what like half of these things mean. I think penicillin is an antibiotic. But then negative text description, so something which it would have a low similarity score with, would be it's a second-generation cephalosporin. Okay. So why would this be useful? Because you can then search for molecules using text, right? You don't need to be necessarily an expert and know all this terminology such as cephalosporins and fourth-generation cephalosporins or contact laxative. That's scary as shit. Contact laxative, I guess that literally makes you poop on contact. I don't know exactly what that means. But, right, I don't know anything about chemistry, but I could go into basically, I could use this model to do this retrieval for structure based on text or retrieve text based on structure. So I could type in, give me a molecule that is a contact laxative, and I could get back this, right? This actual molecule there. So pretty powerful stuff, right? It's basically giving us the ability to interact with chemistry using just text. MoleculeSTM has 2 main properties: open vocabulary and compositionality via natural language. In experiments, MoleculeSTM obtains state-of-the-art generalization ability to novel biochemical concepts across various benchmarks. So it's a state-of-the-art, which is good. You know, I don't You know, I want to make sure I keep you guys up to date with the best papers. So this being the state-of-the-art open vocabulary kind of molecule paper, pretty good. Contact laxative, scary as shit. Yeah, that's contact laxative is also a metal band name. Okay, so that's the first paper, which is going to be about molecules. And like I said, we're going to do both of these kind of at the same time because they're very similar. This is the second paper, and this is actually done by the same group. So if you look here, this guy here, Shengchao Liu, is the same guy here, Shengchao Liu. And both, or I guess the guy, Shengchao Liu, he's this guy. He's also the guy who basically single-handedly wrote all the code for this. And then if you actually go to this guy's like personal website, which you can find, here's his Hugging Face, here's his personal website. He's a joint postdoc at UC Berkeley working with these professors, blah, blah, blah. He's got a PhD in CS from the Mila. But he did all of this in an internship in NVIDIA. I think they mention it at the very end here. So at the end of this paper, this work was done during Shengchao Liu's internship at NVIDIA Research. The authors would like to thank the insightful comments, blah, 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 and the whatever team at NVIDIA. Okay, so this is already starting to paint a picture of like what exactly is going on here. So what exactly is going on here is that NVIDIA, which is the company that makes GPUs, paid this guy, Shengchao Liu, who's just like kind of some generic Berkeley kind of like ML dude, but very high-level Berkeley ML dude, right? PhD CS, postdoc at like very high-level institutions. And then they basically paid this guy to go and then curate some data sets from the massive government databases, right, of UniProt and then PubChem. And then once you curated those data sets, he basically created the clip of molecules and the clip of proteins, which is important stuff, right? Because even just kind of in my field of like computer vision, it seems like 90% of the papers that we read use clip, right? It's like clip is such an important model for stable diffusion. It's important for Gaussian splat stuff. It's important for so many different things that it seems like getting a state-of-the-art clip for chemistry and for biology is actually a huge improvement for everyone, right? And the fact that it's now available, you can just come right here onto Hugging Face, download this model, and just use it. Pretty powerful stuff, right? So we're seeing basically the clip of chemistry, and this is going to be the clip of proteins. So current AI-assisted protein design utilizes protein sequential and structural information. Meanwhile, there exists tremendous knowledge curated by humans in the text format describing the protein's high-level functionalities. So basically the same situation here where you have chemical structures, but then a huge amount of text knowledge that is being ignored. Or you have protein structures, but then a huge amount of text knowledge that's being ignored. Whether the incorporation of such text data can help protein design tasks has not yet been explored. To bridge this gap, we propose ProteinDT, a multimodal framework where the two modalities there is going to be the same thing. It's going to be text descriptions and then protein design, or protein structure. ProteinDT consists of 3 subsequent steps. You have protein clap, which designs the representation of 2 modalities, a facilitator that generates the protein representation from a text modality, and a decoder which creates protein sequences from the representation. We train ProteinDT. We construct a large dataset, Swiss prot clap, with 441 K text and protein pairs. So this is going to be basically the same as the chemistry situation where Swiss prot clap is going to be a subset of Swiss prot, which is a subset of UniProt. Okay, so Swiss prot clap is 400K text protein pairs. That is a subset of Swiss prot, which is a subset of UniProt. And then if we go, UniProt is basically the same thing as PubChem, except instead of chemical compounds, it's basically protein. So if we go hemoglobin here, right? That might not even be how you spell hemoglobin, except give me all the viruses. Okay, here we go. HBB hemoglobin. There you go. I guess it's a Homo sapiens human, taxonomy. I guess it's also all the species too. But here you go. Here's what hemoglobin looks like, and much like there is this SMILES format for chemical compounds, right? So there's this little text-based format for chemical compounds. There's kind of the same thing for proteins. There's basically this text-based protein format, right? So you can see here the protein is basically composed of these amino acids. And one interesting thing that I saw while doing this is, so if you notice this text-based format for this protein is basically just a bunch of letters. And as soon as I saw this, I was like, okay, well, aren't they going to run out of letters? Like, there's probably more amino acids than there are proteins, right? And actually, that's not the case. So a protein is composed of amino acids, right? So an amino acid is about 300 proteins, or a protein is about 300 amino acids, but then there's 21 amino acids, which is like, wait, that's kind of interesting, right? We have 26 letters in our alphabet, and there's exactly 21 amino acids in a string. So that's kind of a crazy coincidence, right? So basically, you can represent proteins as a string of letters where each letter corresponds to a single amino acid, and there just happens to be slightly less amino acids than letters so that you can do this, which is pretty cool. Okay, but what is UniProt? Maybe just a little bit more background. UniProt is a freely accessible database of protein sequences. It comes from a European bioinformatic organization and Washington, D.C. So it's also basically a government database paid for by a bunch of different governments. Okay, so we have two giant government databases, one of proteins and then one of chemical compounds. And this guy created subsets for both of these. And he basically trained CLIP on these subsets. We quantitatively verify the effectiveness of ProteinDT and receive over 90% accuracy for text-guided protein generation and superior performance on 4 out of 6 protein property bench marks for protein property prediction, which is state of the art. They mention it here at the end, but it is better than all current existing things. I think somewhere over here. I'm kind of like jumping through this, so let me know if you need me to slow down here. Okay. So that's both of the abstracts. Maybe let's look at some of the introduction sections here, right? Because we don't really know much about biology. Might as well just read some of these introduction sections. So this is now the chemistry paper. I'm going to actually call it the chemistry paper and the biology paper. So in the chemistry paper, chemical structures of molecules through one-dimensional descriptions, two-dimensional molecular graphs, or three-dimensional geometric structures. This is 3 different ways that you can represent molecules, right? You can represent it through one-dimensional descriptions, which is just a one-dimensional sequence of the SMILES, which we saw. You can represent it as a two-dimensional graph, which is going to be nodes and edges. There wasn't really a good picture of that here, but you could consume a graph with a graph neural network. That's something that people have done for a while now. And then there's also three-dimensional geometric structures, which they didn't do in this paper, but actually seems like probably the most powerful representation, right? Like I said, molecules are fundamentally a three-dimensional thing, right? They live in three-dimensional space. So it seems to me like we shouldn't really be using these one-dimensional and two-dimensional formats of these. But the one-dimensional is very convenient because you can feed it into a transformer, right? So transformers are probably the most powerful model architecture we have right now. But the problem with transformers is that they require a sequence, right? And in order for that, you're going to have to basically, if you have a three-dimensional modality, you're going to have to turn it into one dimension. So, for example, vision transformers, which consume images, which are two-dimensional things, right? In order to consume that image, you have to break up the image into this sequence of patches to turn it into a one-dimensional thing so that the transformer can consume it. So here they kind of basically run into that same issue where, okay, they're going to have to turn a three-dimensional molecule into a one-dimensional string sequence in order to consume it with a transformer. And they run into the same problem here, right, where proteins are even more complicated, right? Because proteins have this, like, this is kind of what a protein looks like, and it's like, I guess it's also 3D. I guess a 3D format would probably be everything you need here, but much like the molecules, like a string, a one-dimensional string is, I feel like, a very primitive way to represent a protein. So that's just immediately something that feels like we could do better than that. Okay. There's also supervised signals, toxicity label, quantum mechanical properties, binding affinity measurements. Those are basically, let's go back here, PubChem. Let's actually go back to our benzene page. So here they're talking about, much like images can have like a class label such as dog or cat or something like that, there's basically a bunch of other supervised labels that you could use in like a supervised format if you wanted to kind of train these things. So for example, this is a benzene is I guess also a benzol, or it's a type of benzol or something like that. But basically there's arbitrary hierarchies of knowledge in which you could classify these things. So you could be using that to kind of like add additional supervised losses for any kind of machine learning problem that you use these things for. However, such a supervised setting requires expensive annotations or predetermined label categories, which is the same thing that we run to in the image world, right? If you want to train a classifier for images, you need to have a data set where you have annotated every single image with the class, right? So that's expensive, and you're going to have to basically pay some third-party service, which is going to pay a bunch of people in some low cost of living area to actually label your images for you. And that's kind of ancient at this point. Existing molecule pre-training methods mostly incorporate only chemical structures, leaving the multimodal representation less explored. This is the text. This vast amount of textual data that is human understandable and easily accessible, right? These things here. We want to leverage this. We want to leverage all this extra text in order to create better representations of these chemical molecules. Okay, we design a multimodal foundation model for molecular understanding that incorporates both molecular structural information and textual knowledge. We demonstrate zero-shot generalization to new drug design objectives using text-based instructions. So you basically design new drugs using text-based instructions, right? So the same way that CLIP, right, by training this CLIP model, right, where you're jointly embedding text and images, allowed the creation of stable diffusion, right? Once you had CLIP, you could create stable diffusion, which allows you to generate an image given a piece of text. So in the same way, now that we've trained our state-of-the-art basically molecule CLIP, we can now create new molecules based on text descriptions, which is pretty crazy, right? We now basically have the ability to create molecules based on a text description, which means that you don't need to be an expert anymore to create molecules. I guess you're not going to be able to do much with just the molecule itself. At some point, you have to actually manufacture it, but that's quite useful. So, how you can create this joint embedding space? You're going to do contrastive pre-training. So this is the same technique that's used for both of these papers, right? So here we go. Here's contrastive pre-training, which is bubble A in Figure 1. A protein clap, a contrastive learning paradigm, aligns the representation space of text and protein sequence modalities. And then here in the chemistry paper, a MoleculeSTM pre-training with two branches, the chemical structure and the textual description. So basically you're taking your structure here, which is either a graph or a string of letters. You're encoding it into this little vector here. So these three little square boxes represent some vector in some embedding dimension, right? And here you're taking the text, encoding it into a vector as well, right? So here's your encoded chemical structure, encoded text information, and you basically want these two to be the same. So here's a little extra projection. So this basically just projects that little vector a little bit further. So now it's just slightly changed, and you're going to be pushing gradients into these projectors here, right? I don't know if they actually push gradients into these encoders. These encoders are basically pre-trained and frozen, and then really what they're training is, or what they're pushing gradients in, are into these projectors here, which just kind of modify the embedding space a little bit. And here's your standard kind of contrastive loss, where you're basically saying, okay, this molecule and then this text, those two should be as close together as possible in this embedding space because they represent the same molecule, they represent similar things. And this other random molecule over here and this other piece of text should be different, right? So you're basically saying this text, this little vector here, and this little vector here, which represents this molecule, these should be far away, right? So you're pulling those apart. And then this molecule here and this text here should be close, so you're aligning those, pushing those together, right? So the contrastive, kind of the easiest way to think about what contrastive pre-training is you're basically sampling random pairs of text and molecules, and you have kind of positive examples, which are things that should be close together in this embedding space, and then you have negative examples, things that should be far away from these examples here, and then you're just basically push-pulling, right? And then you just run that over and over and over and over again with your giant data set here, 280,000 structured text pairs, and eventually you end up with these little projectors and encoders that you can encode a piece of text, you can encode a structure, and then project it into this little latent space, and then use that to do things like structured text retrieval, where you're saying, okay, is the embedding that I get from this little molecule here more similar to the or closer in this latent space to the embedding here, or to the embedding of this text, or to the embedding of this text, or the embedding of this text, right? And you're using some kind of similarity score, such as cosine similarity, right, which is basically just how close those little embedding vectors are. Cosine is the angle between those vectors. So from that, you can say, okay, well, is this molecule for diabetes or gastrointestinal disorders? No, it's more for anti-inflammatory preparations. All right, there you go. Now you can basically use text to look up molecules, or from molecules find the relevant pieces of text. And you can do basically the same thing with proteins. I don't think they have an example for retrieval here, but here's the same contrastive loss here, right? So here you have encoding the text. You're aligning the paired structure with the paired text and pushing apart the unpaired or the negative example. Okay. So we already went over how chemical compounds can be turned into a sequence of letters, which is the SMILE, versus proteins can be turned also into a sequence of letters. And in this case, the letters represent the 20 amino acids. Protein design, ProteinDT stands for protein design with text, where basically right now that you've created this kind of clip of proteins, although they're calling it CLAP, contrastive language and protein pre-training, compared to CLIP, which stands for contrastive language image pre-training. So the CLIP, the I in CLIP stands for image. The A in CLAP stands for LA, language and protein. So I guess they ran into an issue where if they would have called it contrastive language protein pre-training, it would have been CLPP, and CLPP would have just been hard to pronounce. So they decided to just call it CLAP instead for contrastive language protein pre-training. So a little bit different than the naming convention used for CLIP, but they wanted to make it sound like CLIP, right? Because this is effectively just CLIP for proteins. Okay, Emily's got some hints for us. Emily's the one who recommended these papers, and she's the resident bio expert here. Selfies is better than smiles, although not many people use selfies. Okay, so it seems like there's probably multiple different ways of representing molecules with turning it into a one-dimensional sequence of text, and apparently selfies is better than smiles. This lowers the barrier to entry. Yeah, not just lowers the barrier to entry, but just like enables all kinds of future research, right? Okay. Multimodal foundation model for molecular understanding. Our approach, a multimodal molecular model for protein understanding. Okay, so they're ultimately, what are they going to try to do with this? Ultimately, what they're going to try to do with this is this paper is going to go the extra step and actually create effectively the stable diffusion for proteins. So the stable diffusion for proteins, they're going to call it ProteinDT, which is, they're going to try a couple different approaches here. They're going to try an autoregressive approach, which is basically a transformer, and then they're going to try two different types of diffusion models, which they call ProteinDT. So much like stable diffusion uses CLIP to allow you to generate images using language, ProteinDT is going to allow you to generate proteins by using protein clap, which allows you to go from text to proteins. Okay. Let's go back to this one. This is the chemistry paper. MoleculeSTM consists of two branches, the chemical structure branch and the textual description branch. So they call these branches here. Generally, the way that I describe these is I call these kind of like towers or backbones or encoders. So I would say you have a separate encoder for the structure, the chemical structure, and you have a separate encoder for the text, right? Sometimes they're also called backbones. So sometimes you'll see these called the text backbone, the image backbone. Here they're kind of they're calling these branches. So just because it's a different paper, right? It's a paper from a different field, so they use slightly different terminology, but it's like ultimately it's the same thing, right? Such a disentangled design enables MoleculeSTM to be integrated with powerful existing models trained on each modality separately, i.e. molecular structural models and scientific language models. So this is the fact that here they're not actually going to be training the encoder from scratch for either of these modalities. What they're only going to be pushing gradients into with this contrastive learning is into these projectors here, right? So similar to actually the vision language models that we were looking at last week, where in a vision language model you have to basically take a pre-trained vision encoder and then project it into this language token space. Same thing is going to happen here, right? It's like they don't necessarily want to retrain these encoders. They're just going to use some generic pre-trained encoders that they find, and specifically the ones they use. They're somewhere here. Yeah, here we go. PubChem STM, no. Okay, it's somewhere over here. But they use pre-trained encoders, and then they're only going to be training the little projectors. Align such two branches, we construct a structured text dataset, PubChem STM, which is a subset of PubChem. And it's 28 times larger than the existing dataset, which probably tells you why they got state-of-the-art, right? So everybody knows that data scaling is a thing. The more data you have, the better you can scale. So an easy way to get state-of-the-art is to just have a bigger data set than everybody else. And that's exactly what they did, right? They basically just made a giant-ass data set, 28 times larger than the previous one, and then trained a little CLIP model on that. Or CLAP model, I should guess. Or no, in this case, it's called MoleculeSTM. Is trained on a large-scaled structured text pair dataset, and such textual dataset contains open-ended chemical information. To demonstrate the advantages of introducing the language modality, we designed two challenging downstream tasks, the structured text retrieval task and the text-based molecule editing task. Okay, so the two main attributes of MoleculeSTM is what they call open vocabulary and compositionality. And this is like, it's a little bit, it sounds confusing, but it's actually, you have a very good intuition about what this means. So what they're talking about is that because you're now using language, just generic text and structure, there's no limit to what you can type in here, right? So basically it's open vocabulary in that you can type whatever you want, right? You can express, or you can a wide range of biochemical concepts with the unbounded vocabulary depicted by the natural language. So there's nothing that's preventing you from typing in a molecule that gives Shrek his green color, right? You could literally type that, encode that, and this will produce some structure. Granted, it might not be a useful structure. Maybe it gives you the molecule that results in the green color of like a chloroplast, right? But it's open vocabulary, right? You can literally type anything in. And that's kind of the magic of stable diffusion, right? Is that you can generate images with open vocabulary, as in you can use any text that you want. So now they're saying, okay, well, now because we've effectively made the clip of molecules, which they call MoleculeSTM, we can now use open vocabulary which is no longer limited to some fixed set of predefined molecule-related textual descriptions. You can literally type whatever the fuck you want in here. And not only can you type whatever the fuck you want, you can also do what is known as compositionality. Compositionality implies that we can express a complex concept by decomposing it into several simple concepts, right? So you can generate molecules that satisfy multiple properties simultaneously. And again, this kind of sounds a little bit confusing, but what are they talking about? They're saying that because the text is completely open, you can say, okay, I want a molecule that is green and then also has a carbon ring or something like that, right? So you can compose multiple concepts in much the same way that whenever you use stable diffusion, you can say, hey, I want an image of Shrek, but I want Shrek to be holding a GPU, right? So you can compose multiple visual concepts into a textual description, and because of clip, stable diffusion will now be able to generate an image of Shrek holding a GPU. So compositionality and open vocabulary are now available for molecules themselves, which is pretty powerful. Furthermore, for molecular editing tasks, visual inspections reveal that MoleculeSTM can successfully detect critical structures implied in text descriptions. MoleculeSTM can improve the performance, blah, 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 via fine-tuning. MoleculeSTM achieves the best overall performance among 9 baselines on 8 property prediction tasks. So what are they talking about here with improve, where is it? Zero-shot classification. So basically they're saying, okay, well, now that we've created this molecule clip model, right, can we determine that it actually could be used for a previous benchmark? And that's actually very similar to what they did in the original clip paper. So in the original clip paper, right, they train this contrastive language image pre-training model, but you can use this contrastive language image pre-training model to see if you can solve some kind of generic classification task, such as ImageNet, right? So they're like, okay, well, what if we feed just these images and then use our clip model in zero-shot to classify them, right? And you get 76.2. So versus if you just trained ImageNet in its standard supervised form with a ResNet 101, this is like a kind of an old school residual network, old school architecture, you get 76.2. So this is a little bit of a proof of concept here, right? Where now you take a model which has been trained on this contrastive learning objective, and you're saying, okay, well, the embedding space that I've created there, can I use it to just train a little classification head on this older benchmark and use that as a way to validate that this embedding space that I've created is actually has like some kind of like meaning to it? And the answer is yes. Look at that. Boom. Not only that, but you actually get state-of-the-arts. So look at that. You're getting state-of-the-art results on older benchmarks where people were having a hard time, right? So people were trying to solve ObjectNet using a ResNet 101, just training in a standard supervised manner, and they were getting a score of 32, versus now you're using clip. You're not even training on this. You're training on some other thing, the contrastive language image pre-training, and with a zero-shot kind of a little classification head, you're already getting state-of-the-art on this old-school benchmark. And that's basically what they're saying here, is that, okay, they took this MoleculeSTM, which is trained contrastively, and then they're like, hey, can STM improve the performance on standard molecular property prediction benchmarks, which I assume is some kind of like classification type benchmark that's probably been around since forever. Actually, if we click on 9, here we go, 2018. So some 2018 benchmark, a benchmark for molecular machine learning, which I guarantee you is some kind of supervised learning generic classification thing. And here they are getting state-of-the-art results on these old classification benchmarks using their contrastively trained MoleculeSTM. So basically the same thing that happened with clip. So I think that's kind of cool, right? It's like this, there's just like more and more pieces of evidence showing that this MoleculeSTM is literally just clip, which was, I guess, 2021, and now it's 2024, so it's a little bit, it takes a little bit longer, or it took a little bit of time for clip to be reproduced for molecules instead. How's it going, 87? How's it going, Aries? Okay, so let's jump into the protein paper, which is largely going to say the same thing here. We consider 3 downstream tasks to verify the functionalities of ProteinDT. So they do text-to-protein generation. So you go much like text-to-image models. Here you're going text-to-protein models. So you generate a protein given a piece of text. Generate protein sequences from the input text prompts, which describe the desired protein attributes. The second task is zero-shot text-guided protein editing. So very similar to this task here, right, where you're doing the molecule editing, where you're basically given some prompt, you basically edit part of the molecule. They're going to be doing the same thing with the proteins, although it's a little bit more complicated. So for example, here's your input protein, and then you give it the prompt, more alpha helices. I don't really know what an alpha helix is, but I assume it's probably this red shit here. So you give it this prompt, more alpha helices, and it basically edits this protein, and here you go. Here's the same protein, but with more alpha helices. Pretty badass. Look at that protein editing. I don't know. This, like, there's so much shit that's going to come out of this. You know, it might even be the case that all the, like, next level longevity stuff, like the reason we have immortality is going to be some paper, and in that paper where they describe the way to get immortality, they reference this protein clap paper. They reference this MoleculeSTM paper, right? So it's kind of exactly what I was saying before, where like CLIP is used everywhere in computer vision. I wouldn't be surprised if this MoleculeSTM and this protein clap ends up being everywhere in bio and chemistry, right? So it's time to buy stock in this guy here, this Shengqiao Liu stock. Buy stock on this guy because he's going to get cited 1 million times for both of these papers. Okay. So ProteinDT also, compared to 6 state-of-the-art protein sequence representation methods, ProteinDT obtains consistently superior performance. So also state-of-the-art interpolation in the sequence-level representation space. Okay. Zero-shot protein design, editing based on textual descriptions, dataset construction, and 2 modalities. So let's look at the way that these datasets were created. MoleculeSTM consists of the chemical structure branch, textual description branch. Again, I call these encoders or just backbones. I don't know why they're calling them branches. I've never like heard that specific format, but you basically have FC is going to be the chemical structure encoder, and then FT is going to be the text encoder. MoleculeSTM maps the representations extracted from these 2 branches to a joint space using 2 projectors, PC and PT. So that's where they're actually going to be pushing these gradients. The little projectors are, I think, just little multi-layer perceptrons, so just a little tiny little neural net. We need a fantasy board to track these researchers. Yeah, you could. I wonder, you know, when I think about like what an open science world looks like, right? At some point, we're going to kind of break free of these institutions, and we're going to have science that is more decentralized and open, right? Like, how would that world work, right? Well, in that world, you might be able to like invest in researchers, right? So you might be able to say, hey, I'm going to invest some money in this researcher. They use that money to do some research and publish it, and then whenever people use that research, that person gets some small amount of money, and I get some small amount of money from that. So it's kind of weird to think about that, but I wonder if we're going to maybe see like almost like a VC business model for individual researchers. But before that even happens, we need to kind of get rid of this like institutional kind of control, right? Because right now, academia and research is like very tightly controlled by these publishing journals and then the institutions themselves, and what you work on, what you don't work on, and who gets credit, who doesn't get credit. And the way that you get rewarded is that you do research, you publish that research, you get cited for that research, and if you have more citations, it's easier to raise money to do more research, right? So it's a little bit, that seems like a little bit of a convoluted process. It's probably more simple to just kind of get rid of all the intermediate kind of bureaucracy in that and just have people directly invest money in researchers, but I don't know, we're still probably a couple decades away from that. Okay, so again, the chemistry one is going to be trained on this PubChem STM, which is constructed from PubChem, and then the protein 1 is going to come from SwissProt-Clap, which comes from SwissProt, which comes from UniProt. We note that the dataset size of SwissProt-Clap is relatively small compared to the peers from other domains, e.g. 400 million text-to-image pairs in the language vision domain. So this is also another kind of like good thing here, right? Is that even though both of these papers represent the state-of-the-art for basically a CLIP model, a language protein and a language molecule model, they're not even that big, right? So these models have really only been trained on less than 1 million pairs of text protein and text molecule. So there's probably another 10x improvement just waiting here for whoever is willing to go into UniProt, right? The raw UniProt and then the raw PubChem, download literally all of it, right? Rather than just some subset of it, right? Look at this. PubChem contains more than 150 million substance descriptions, 225 million biological activity results. So we're getting state-of-the-art results with 281,000 text pairs, right? There's another 225 million pairs just sitting there on this database waiting to be used. So pretty good stuff there, right? It means that even though this is state-of-the-art, it's still not even the beginning, because we could even get another 2 or 3 orders of magnitude in the data set, and 2 or 3 orders of magnitude in the data set size is like, we're going to get easily a 10x performance improvement on the models themselves. Okay. Protein sequence XP and representation ZP. So proteins have four levels of structure: primary, secondary, tertiary, quaternary. I think this is like the 4 different types of folding. The primary structure is XP, is the sequence of amino acids, and that's basically what you can turn into a sequence of letters, which is what you can then use feed into a transformer, right? The transformer requires a one-dimensional structure for the data, so you're not going to be able to describe the secondary, tertiary, and quaternary structure of this protein in one-dimensional way. So they really only focus on this first part, which tells you that we still have a lot of space to grow there as well. We use BERT as the encoder. So this is something that I thought was a little bit sketch here, is that they use BERT for both of these papers, but like the way they describe it, this seems like they're they're aware of the fact that this is kind of sketch. Let me see if I can find it. MoleculeSTM. Let's see. BERT. All right. I can't find it in this first paper, but it's here in the second paper. But they say, for the protein sequence representation, so going from this protein sequence, which is basically a string of letters representing the amino acids, we're going to encode that with FP, which is our encoder, and we're going to turn it into a latent representation or embedding, or basically just a little vector of numbers called ZP, which they're calling the protein sequence representation. We're going to use BERT as the encoder. BERT is not one of the most advanced transformer models. And that's kind of what I thought was funny here, is that in both of these papers, they use BERT, which is actually like low-key shit tier transformer. Nobody uses BERT in MLP anymore, or NLP anymore. Nobody uses BERT in pretty much any task requiring language, right? So this is kind of old school that they're using BERT here, right? But I don't know. Even more room for improvement, right? Imagine training something that's not BERT on 10 times the amount of data. Probably get a lot better performance. We take the BERT model with ProtBERT pre-training, and this is why they're using BERT, right? So why would this guy this guy who's literally worked at fucking UC Berkeley and has a CS PhD degree at Mila, why would this guy be using BERT, right? Doesn't he know that BERT is shit? He does know that BERT is shit, but the problem is that he wants to basically train these projectors here, right? He doesn't want to train this encoder from scratch, right? Because pushing gradients into that encoder is going to take fucking forever. So he only wants to train these projectors, right? So he's going to keep these encoders there, and he's going to use pre-trained frozen encoders. But the pre-trained frozen encoders that exist for protein stuff, they're not like super high level, right? So like the only option that he has is ProtBERT. And ProtBERT, if we go to 7 here, ProtBERT is 2020. So he's kind of stuck here, right? He's basically saying, okay, I wish I could have used a better transformer and trained this from scratch, but I don't got time for that, so I'm going to have to start from some pre-trained model, and the only pre-trained model that's available that is based on the transformer architecture is based on this kind of older transformer architecture called BERT, and hence I'm going to use BERT. Okay. ProtBERT is pre-trained on a large protein sequence corpus, blah, blah, blah. Okay. The text description. So now we know what the encoder for the protein sequence is, but now we need an encoder, FT, that consumes the text description, XT, and produces a text embedding, ZT, right? So the encoder here, ProBERT, or I guess let's go ProtBERT, right, which is the pre-trained BERT for proteins, consumes the protein sequence, which is literally just a string of letters, and then it produces this little vector here, this embedding that represents that protein. The text encoder, which comes from PSI-BERT, let's see, right here. God, I'm like dancing all over the place here. I think it's this. Yeah, ProtBERT is the pre-trained encoder for the protein. The pre-trained encoder for the text comes from PSI-BERT, which was pre-trained on the full-text computer science and biomedical papers from Semantic Scholar. So PSI-BERT seems pretty strong. They probably could have used other ones. I think there's other models that have been pre-trained on very large, kind of broad science and biomed papers. So I feel like there's probably a better one here, right? So there's a lot of different things in this paper where they could have done better. They could have used a much bigger data set. They could have used encoders that were trained from scratch on the much bigger data set, and they could have used a better model architecture for both of these encoders. So that's a good thing, right? It means that there's a lot of room for improvement. Although both modalities use BERT-like models, the detailed architectures and token vocabulary are different. Obviously, the token vocabulary or the dictionary of possible tokens for the text encoder is going to be like text tokens, right? Like little chunks of sentences, little chunks of words. But the token vocabulary or the dictionary used for the protein sequence is going to be basically these amino acids, of which there's only 20. Further, such a disentangled design allows us to adopt the respective pre-trained models to mitigate the limited availability of structured text sequence protein pairs for training. VR Wizard. Creating designed proteins is interesting for the field of synthetic biology because we can insert genes into bacteria very easily and the bacteria produce it. Yeah. It gets pretty crazy, right? Because it's like, think about like something like Stable Diffusion, right? Text to image models are so powerful because art used to be extremely difficult, right? It's like there was a very small set of people in the world who could create art, right? But with text to image models, you can now be some random you could be someone with zero artistic skill and just go into Stable Diffusion and just type in, I want an image of this, and it's a fantasy image, and blah, 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 and boom, you get it, right? So you're able to create art using, as they said in this paper, using open vocabulary and open and compositionality, right? You can describe whatever you want in text, and you can compose multiple concepts in text just together, right? You can say, I want the Shrek holding the GPU with the background is mountains and everything is in Picasso style, right? you're going to be able to do that with proteins and molecules, right? So the good side to this is that you're going to have a bunch of people who don't know anything about biology and chemistry being able to basically create new proteins and new molecules using just text description. The negative side to that is that people will be able to just type in, give me the most poisonous poison that will instantly kill someone, and it'll just like output that. So it could be a little bit dangerous, but I generally tend to think the good of a technology will outweigh the negative of a technology, but we're entering a new world. Okay, let's go back to this paper. You still have to synthesize it in a lab. That is true. Emily is correct. If I just type that in, I wouldn't even get this, right? I wouldn't even get this molecule. I would basically just get this. And like, if I don't know anything about chemistry, this is effectively useless to me. It's like I have no idea how to synthesize CC parentheses equals O, OC1, C, like, you know, I have no idea how to make that. But, you know, I think we're probably just 10 years away from some kind of robot where you can literally just input this and then the robot produces it for you, right? I don't think that's that far away either, right? Imagine like a little terminal where you go and there's just a computer with a keyboard and then there's a little robot inside this glass box and it's sitting there and there's all these little vials in front of you and you just go in there and you type in OC1CCCCC1 and then the robot goes like and then it goes and it just like sits there and it starts mixing little test tubes and then it goes like and it opens a little slide door and it gives you the little vial containing OC1CCCC1. Designer drugs. Okay, so we're looking at MoleculeSTM, MoleculeSTM's data set. Open vocabulary, language is by nature an open vocabulary in free form. The language model has proven its generalization ability in various art-related applications. Here's the Stable Diffusion citation right there. Our method is not limited to a fixed set of predefined molecule-rated annotations, but can support the exploration of novel biochemical concepts with unbounded vocabulary. Blah, blah, blah. Retrieve the drugs with the highest rankings. Right, so you can use text to search drugs. The compositionality, complex concept can be expressed by decomposing it into simpler concepts, such as a molecule is soluble in water and has high permeability. And then you can use that to search a whole database of molecules and get the best hitting molecules. With the pre-trained joint space between chemical structures and textual descriptions, MoleculeSTM can transform the molecule property compositionality problem into the language compositionality problem, which is more tractable using the language model. Right, so language being inherently compositional. For the zero-shot retrieval, we construct 3 data sets from DrugBank. DrugBank is by far the most comprehensive database for drug-like molecules. The description field, the pharmacodynamics, and the anatomical therapeutic chemical field. So this is a experiment, right? So much like in the clip paper, they basically tested out the goodness of the representations that they get from this clip style training by benchmarking it on an ImageNet classification task. They're doing the same thing here. They're basically going to go into this drug bank and they're going to basically create a test where they know what the description of the drug is, they know what the pharmacodynamics is, which is also a text-based description, and they know what the drug is, and then they're going to feed this text into their MoleculeSTM. MoleculeSTM will create an embedding vector, and then they can also feed the drug itself into the MoleculeSTM. It'll create another embedding vector, and then they can use the similarity score between those embedding vectors to then determine the basically, is it correctly saying that this text and this molecule match? And here you have the structured text retrieval result, so the result of that experiment. Drug bank description. So based on the description, can you find high similarity and get the right molecule, right? So you look here. This is using the smiles versus the graph. So the graph is going to use the encoder that looks at the graph-based representation of the molecule. The smiles is going to use the encoder that uses the text sequence-based representation of the molecule. And you can see Here, frozen, which is these red bars, is kind of like the baseline. Frozen means that you don't use these projectors here. You're basically just relying on the pre-trained frozen encoders, which come from some generic pre-training that was done years ago. And you can see how the MoleculeSTM, whether it's done with the smiles or whether it's done with the graph-based structure, it's the highest one, right? So you can see here the accuracy, which is how accurately can you find the correct molecule given the description, very close to almost like 100% here, right? You can actually see that the difference between the graph-based structure, which is this hatched pattern, and then the smiles, which is this solid pattern, is actually not that much, right? So whether you use, it doesn't really seem to matter how you encode the structure of it, right? Either way, it's way better than the embeddings that were created from these pre-trained frozen encoders, right? So look at that. That's kind of a visual representation of just how state-of-the-art it really is, right? You went from basically 50% to 100%, which is, conversely, also very similar to the improvements that you get with the original clip model. So it's almost like history is repeating itself. Okay. Given chemical structure, retrieve the textual description, or the opposite of that, given textual description, retrieve chemical structure, and then the retrieval accuracy is used as the evaluation metric. And then the baselines are basically using the frozen pre-trained encoders. Okay, the graph representation has a higher accuracy and the smiles representation, but they kind of trade off. So you see here, they're kind of about the same here. Here, this one is a little bit higher. Here, this one's a little bit higher. What that tells me is that there isn't much of a difference between the smiles and the graph representation. And I think that what they should have done is they should have figured out some way to do this three-dimensional. Like, that seems to me like another missing piece here, right? It's like they're comparing smiles, which is one-dimensional text description, to the two-dimensional graph description, but both of them seem to be performing about the same. Right? So what's left to test here is, hey, can we figure out how to make one of these that encodes a three-dimensional geometric structure into an embedding vector, and then see where that lands here, right? Like, I wonder what the three-dimensional one is. Is it higher than pretty much all of these? It's kind of cool. Or it could be cool. Pipelines for zero-shot text-based molecule editing. Let me drink some coffee here. Very noob question. What do you mean by synthesize it? Do you mean creating the protein? Can you create any protein as long as you know the sequence? Is it just a matter if the protein is useful or not? I do not know the answer to that question, but Emily does. I presented this example of like this kind of magical robot machine where you just give it a sequence and then it produces the protein, but I feel like it's probably way more complicated than that. There's probably specific types of proteins that are easier, and then like the ingredients for it are also probably like important, right? There's certain types of ingredients that are probably easy to get, certain types of ingredients that are hard to get. So synthesis still seems like a hard problem. This is what a protein sequence looks like, by the way. So this is an examples of text protein pairs in the Swiss prot clap, which is the subset of the uniprot. Basically, you have your text-based protein sequence, which only captures the first level of protein structure, right? As they said, there's 4 levels of protein structure. The first one is just the sequence of amino acids, but then you have this like secondary, tertiary, quaternary structure, which is like the folding, which is way harder to do, right? So like the AlphaFold from Google DeepMind, what they do is they get a sequence of proteins. So basically they get this, and then they try to determine the actual like secondary, tertiary, like the actual folding, right? So you see how all this folds. But in this paper, they don't try to do any of that. They're just working in this like pure text space or single text sequence space. Look at that. Okay. Let's go back to here. Text to protein prediction. Oh, no, we were looking at the zero-shot text-based molecule editing. Okay, so now we want to edit molecules based on text. So we have a molecule, we want to edit it on text. So here, binding affinity-based editing, drug relevance editing. Here's your results. Visualization results for the zero-shot text-based molecule editing. Satisfactory hit ratios of 4 types of text-based editing tasks. Single objective, 4 multi-objective. I think they describe exactly how they do this. Chemical structure branch. So this is also weird. It's like the way that these bio papers work, the description, the method section, which is normally kind of like, normally in an ML paper, you have the abstract, you have the introduction section, maybe you have a background work section, and then you go straight into basically the method section, right? But that's not how these bio papers seem to work. In the bio papers, they go abstract, they describe the actual results first, and then you have to scroll down past the conclusion. So they actually literally give you the conclusion. The conclusion is called the discussion. And then once you're done with the actual discussion and the conclusion, then they give you the method. It's kind of a weird format, but then here, after the conclusion, you get the actual method, which is where they actually give you all the details. So for example, the fact that the deep learning encoder FC, which encodes the chemical structure, comes from the megamole BART. So this is the pre-trained encoder for the chemical structure. And then the pre-trained encoder for the graph-based chemical structure comes from this graph MVP training, which was trained on the Geom dataset. The textual description branch FT is a BERT model and actually uses the same pre-trained SciBERT. So that's kind of interesting. Both of these papers, whether it's the chemistry paper or the biology paper, they're both using SciBERT as the text encoder. So this orange vector, or this purple vector here that comes out of SciBERT is actually the same as this vector, this kind of red vector here that comes out of this encode FT here. So kind of cool. They're using the same text encoder for both of these, which actually isn't even the best text encoder, right? As we were saying, it's kind of like an old transformer architecture. Okay. Contrastive pre-training. Okay, maybe let's do a little dive into contrastive pre-training. So the same thing with this molecule paper, you have to go all the way past the conclusion to get to the method section. Here they have a little method section on diffusion models, on autoregressive models, which is kind of like a transformer. Here we go. Protein clap, which is the contrastive language image pre-training, except now it's contrastive language protein pre-training. So what is contrastive training? And I think here's where I'm going to bring in this. So contrastive learning, contrastive representation learning, this is comes from Lillog. Lillog is like this blog written by this person, Lillian Wang. And this is a very good blog and very intense. As you can see, it's like extremely heavy. You know, you probably couldn't read this in one sitting. You're going to have to read this in multiple sittings. But there's only one part of this that we're really kind of interested in, right? We're interested in specifically the kind of most generic explanation of what the fuck is contrastive learning, and basically comes from this. Noise contrastive estimation, short for NCE, is a method for estimating parameters, blah, blah, blah. The idea, okay. So noise contrastive estimation is what they're going to be using here. There's 2 different loss functions that are used for this type of contrastive learning, EBM NCE and info NCE. And both of these papers are going to be doing the same thing, right? They're basically either using EBM NCE or info NCE, right? And the simplest way to really explain the difference between those, as they say here, the difference between EBM NCE, EBM stands for energy-based model contrastive learning. What is the N again? Noise contrastive estimation. Noise contrastive estimation, energy-based model noise contrastive estimation, and info noise contrastive estimation. The former performs binary classification, so EBM is basically classifying into data, not data, and then multi-class classification for info NCE, where you have multiple negative examples, right? So with any contrastive learning approach, right, you're basically saying, here's an example, here's things that I want to pull together, and then here's things that I want to push apart, right? So here's the NCE. I think the info NCE here is a little bit better. The info NCE loss uses categorical cross entropy to identify the positive sample among a set of unrelated noise samples or a set of negative samples, right? So I think there's an image here that I want to show. Yeah, so here, for example, how would contrastive learning work in images, right? So for images, you would have, here's your image, and here's going to be your positive example, which is also basically a cropped image of the same dog. And then here's going to be your negative examples, right? So whenever you take this image and you feed it into your encoder, right, you're going to get a vector. The vector that comes out of that image and the vector that come out of this image should be the same. It should be very close together, right? Because they represent the same dog, right? It's basically saying the vector that comes out of this and the vector that comes out of this should align. They should be close together. The similarity score between these should be very high. Versus the vector that comes out of this and the vector that comes out of this should be very different, right? They should contrast. They should be far apart. The similarity score should be low for those, right? So that's effectively what you're doing. Set of unrelated noise samples. Given a context vector C, the positive sample should be drawn from the conditional distribution, while n-1 negative examples, there's different amount of negative samples that you can pull. In this case, they're just using one negative sample, right? So they're just basically just one negative example, one positive example. I guess there's two negative examples here. One is the text description, and then one is the actual molecule. But you can have many more if you wanted to do that. There's lots of different types of contrastive learning. The info NCE loss optimizes the negative log probability of classifying the positive sample correctly. So here, the probability of getting this vector given this conditioning versus the summation of all other negative examples, where here you see you're summing over all your negative examples given that conditioning, right? So as they were saying here, right, the difference between EBM NCE and info NCE is that the former predicts binary and the latter conducts multi-class. So binary means just two, right? You have the positive and the negative example. So here's the XP and then XP and then XP prime here. So your negative example and your positive example versus info NCE, you're summing over all of them. So you see how here now, these look very similar, right? It's just kind of like your generic classification stuff. But here, you just have one positive, one negative. Here you have a summation over, you see that? You see how there's a little summation sign over that? So they're kind of basically the same thing, just a little bit different. But ultimately, the only thing that you really need to remember is this kind of intuition of pulling things together that are similar and then pushing things apart that are different. So that is contrastive learning. Or the contrastive pre-training, same thing going on here. Align the structured text pairs of the same molecule and contrast pairs from different molecules. The energy-based model, NCE, requires this energy function. So that's really what you're trying to shape. You know, you're basically saying the energy of data versus stuff that's in the data distribution versus stuff that's not in the data distribution. But they literally use the dot product of the embedding vectors as the energy function. And I had to look this part up here, but this is like kind of a weird, like this thing here. So PC, and then I was like, what the fuck is that? A little circle FC. And I looked it up, and it's basically compositional. Here, let me actually pull it up. Control T, GPT, open up this. Give me this. Yeah, that's what I want. So this little thing here, this little open circle, is the function composition function, which is basically this. So rather than saying, okay, you have some input x, you apply the function g of x to it, and then you apply the function f of x to it, you use this notation, which just seems more confusing to me. So that's what that means there, is that you're taking your XC, your input chemical structure, you're encoding it with your FC, your encoder for the chemical structure, encoder's FC, and then you're passing that into the projector right there. But why use this notation? This is just unnecessarily complicated. Just literally do PC parentheses FC parentheses XC close parentheses close parentheses. You know, like why use this fucking function composition function? Like, what's going on, guys? I don't know about that. I don't know about that choice. Okay. Space alignment. Maybe we can talk about this. So, text-based molecule editing, molecular property description. Okay. Pipeline for zero-shot text-based molecule editing. Okay, so how are we going to be doing this molecule editing? So you're going to have two phases. It's a two-phase process. In step 1, or phase 1, your space alignment aligns the representation space of our pre-trained molecule generation model and the representation space of MoleculeSTM. So there's some pre-trained molecule generation model, right? Some model that auto-regressively generates the next little token in your sequence of molecules. So there's some pre-trained model here which generates here we go. The goal is to learn an adapter module to align the representation space of the generative model to the joint representation space of MoleculeSTM. So the joint representation space of the MoleculeSTM, this is your like clip space, right? This is what's actually coming out of your MoleculeSTM. Your MoleculeSTM has the ability to project XC into some shared space in which you can also project XT. But that representation space is going to be different from the representation space of your generation model, right? Your generative model. So in order to basically use both of these models together, you're going to have to learn this thing here, which is also kind of like a projector, right? You're basically learning this function here, which will map this embedding space here, or this vector here, which comes out of this encoder FG, with what comes out of this encoder FC combined with the projector PC, right? So if you remember, this encoder is some pre-trained thing. This encoder here is some pre-trained thing. This projector PC here, this is what comes out of the contrastive pre-training, right? So here they push gradients into this and got this. And now you want these two to kind of match. So that's why you're training this MG2F. And that MG2F is adapter module. It's also a little multi-layer perceptron, I'm pretty sure. But once you have this alignment module, then you can now take a molecule, you encode it, it's now a vector. That vector, in order to compare it with this text, right, so you can take text, encode it with FT, the same way you encoded this molecule with FC. You project it with PT, the same way you projected this with PC. This vector here and this vector here are basically, should be very, very similar, right? But this vector here is not in the same embedding space as this. So in order to compare it to this, you're going to have to basically use this align M2FG here so that you can compare this with this, right? So you compare that with that. You say, okay, well, actually, this one is a little bit different than this one. It's the distance, this vector is here in the embedding space. This vector is here in the embedding space. I want to move this one closer to this one. Therefore, I'm going to push a gradient that adjusts this vector here such that it's closer to this vector here, which ultimately is basically moving this molecule here and editing it so that it's closer to here. So how is that editing happening? It's happening because this molecule here is represented by some encoded vector here, right? This vector, if you fed it into the generation decoder, it would decode it into this molecule here, right? So in order to edit this molecule, you're basically taking this vector and then moving it in the direction of this vector. So you're basically saying, I want this vector here, but take a couple steps in the direction of this vector here. And then you'll end up with a new vector. And if I take this vector, which is going to be different from this vector, this kind of makes it look, this should be a slightly different color because this vector is going to be different from this color, or this vector. And if I decode it, it's going to be close because it's going to be similar to this vector,
right? But it's going to be a little bit different, right? It's moved a little bit in that embedding space. And now you can see how there's a little bit of a difference here. You see how this part here changed? So now it's like this OOH, now it's this OO and whatever this is, carbons, I think. So when you decode it, now you're going to get a slightly different molecule, and you can basically say that we've edited the molecule, right? So it's a little bit different than like image inpainting, right? In image inpainting, when you're using a generative image model, you're zeroing out a specific part of the image, right? You're masking out a part of the image, and then you're reconstructing that part of the image, right? Versus here, what you're doing is you're basically moving in this latent space, right? Based on, you're projecting a piece of text into the latent space of this generative model, and then you end up with 2 points, and then you're moving in that little latent space, and then just basically taking the point at which you end up after a couple little steps of this optimization, and then decoding that, and you're going to end up with some molecule, and that molecule is going to be hopefully an edited version of this one, right? But here they make it look like it just edited a little part of it, but it could be the case that as you're taking little steps in this latent space, you cross a boundary, and then whenever you decode it, you end up in a place that's almost like completely different, right? So this makes it seem like it's a very precise editing process, but you could, through the process of optimization and moving around in the latent space here, you could end up in a completely different place, right? I don't really know what the latent space of these molecules looks like, right? And maybe that's a good place to talk about this. So when I keep mentioning latent spaces and embedding vectors and like, what the fuck am I talking about, right? So what I'm talking about is this. This is a space of protein molecules, right? So things that are close together here are related, right? So we look at this point, this corresponds to this molecule. We look at this point, this corresponds to this molecule. So whenever you're editing here, what you're doing is you're basically, you see here how they're saying latent optimization steps, right? You're moving in this latent space. So what does moving in the latent space means? It means that you're here, and then you're taking a little step, taking a little step, taking a little step, taking a little step, and then you end up at some point here, and then you feed whatever this latent vector is here into the decoder, and the decoder will give you some molecule, right? So latent spaces this is like a dimensional reduction of it. So this is like a 2-dimensional latent space, but the latent space of this is much higher, right? This is much more than just 2-dimensional. This is probably 128-dimensional, right? So it's kind of hard to think as a human what a 128-dimensional latent space even looks like. But in your head, imagine something kind of like this, right? Where there's basically you can move around here, and then different areas kind of represent different types of molecules, right? But that's how they're doing the zero-shot text-based molecule editing. Given the input molecule Cin and a text prompt, the goal is to optimize a latent code W directly. The optimal W, the latent code W is this here, right? This is your latent W. Optimal W should be close to the representation of Cin and XT simultaneously, right? So basically you want this to be close to this and also this. You want it to be close to your text description, which is your edit direction, if you want to think of it that way, and also be close to the original molecule. The problem with these type of things is that there's a lot of like a little bit of massaging here, right? Because, for example, here they're using a cosine similarity loss here, and then they're also using an L2 loss. So cosine similarity is basically like the angle between these vectors, right? L2 loss is the basically taking each element of those vectors and then taking the L2 difference between those. So slightly different ways of measuring similarity. And then you have this arbitrary kind of hand-chosen hyperparametering here, which basically says how much more do I care about the cosine similarity as opposed to the L2 similarity. And this is kind of what I mean by there's a little bit of bullshit here. It's like whenever you're moving in this latent space, you're taking some amount of steps, you're using these similarity metrics, which are already kind of fuzzy inside a latent space that itself is already kind of fuzzy, and then you have this arbitrary balance between these arbitrarily fuzzy metrics in an arbitrarily fuzzy latent space. So it's fuzzy, right? It's ultimately, I guess, what I'm saying. But
you run this optimization, you move around in this latent space, right? You move a little bit, and then you end up in some new place, and then you can decode that, and you get your edited molecule. All right. So that was the zero-shot text-based molecule editing. And then we can see here visualization results for the zero-shot text-based molecule editing. Satisfactory hit ratios for 4 types of text-based editing tasks. I'm not exactly sure what satisfactory hit ratio is. It's like probably some kind of metric of like, did it actually do the thing that you wanted it to? You know, so like here you're saying, okay, I want this molecule to have high permeability. So there's probably some like heuristic way to determine whether a molecule has permeability. So hit ratio is probably like, did it actually achieve high permeability or did it not achieve high permeability? I'm not really up to date on my chemistry and biology benchmarks, but higher is probably better, lower is probably worse. For ChemBL, okay, so these are a bunch of different benchmarks that use this satisfactory hit ratio. Okay, and you can see here we have random, so taking a random walk, I guess, versus a MoleculeSTM using the smiles, and then MoleculeSTM using the graph-based representation. So the 2 different types of MoleculeSTM, and obviously you can see that this blue and this dark blue are the highest, but not even that much, right? So for example, you have some molecule, and then you have your molecule, and then you give it a text description. The text description is, this molecule is insoluble in water and has more hydrogen bond donors. So you've basically taken that text description, turned it into a vector, and now you're going to take whatever your original molecule is and kind of move it in the direction of the embedding vector that represents molecules with that are insoluble in water and have more hydrogen bond donors. And you can see that you kind of end up, I guess, having a higher hit ratio, which means that your edit is correctly editing the molecule such that it has these desired properties. So this is kind of cool because it means that, right, imagine if you took like some kind of, like somewhere there's a database of all the different psychedelics and all the different properties of the psychedelics, right? So using this, you could put in one psychedelic here. You can take a psychedelic, put the compound here, encode it, and then you could say, I want to see purple elephants. And then that would somehow project, right? Because it's open vocabulary. Open vocabulary means you can put anything you want in here. You're going to get some vector that represents the ability to see purple elephants. Might not be super meaningful. And then you can move the molecule of that psychedelic towards that editing direction, and it'll tell you what edit you need to do in order to get a new type of psychedelic that allows you to see purple elephants. And obviously that's kind of like a bullshit example I just came up with there, but that's the power of this kind of like molecule-based editing, right? Is that you're going to be able to take existing compounds and kind of move them in a direction that you're interested in. And that direction that you're interested in doesn't need to be described in some complicated way. You can literally describe it like this. This molecule looks like caffeine. This molecule is soluble in water. So let's say you have a drug that you're trying to sell, but it doesn't mix in water nicely, right? You want something that achieves the same effect, but that people can mix in their water so that it is soluble and mixes in water nicely. So you could literally just put that text description, move in this latent space, and end up with a new molecule that's soluble in water. Pretty cool stuff, right? What if there is no similar candidate texture that is matched to our similarity? Let me see, I can't really see your thing. What if there is no similar candidate texture that is matched to our smile input? Text? I think that's what you meant. When you do smile format to generate text to match similarity between text and smile, how can we give a list of textures, text to measure similarity? Do we need hundreds of lists of texts? I'm having a hard time understanding your question, Sakun. But for every, in these databases, all the molecules
have basically text associated with them, right? So for example, here, benzene, right? There's some molecule that represents it, which is this little text, but here there's the description for it. So this is the text, right? So you can see, for example, flammable is here, natural process, United States, right? So you could probably type in this molecule was made in Russia, right? And then it'll give you an embedding vector that represent molecules that have the word Russia in their text description. What that means, I don't know, right? It's like, as I was saying before, it's like these latent spaces, it's very hard to interpret what it means, right? It's like it could be the case that like stuff over here is like molecules that are flammable, and stuff over here is molecules that are water soluble, right? So if you take a molecule that is flammable that's somewhere over here and you say, okay, I want it to be water soluble, it'll start moving in this direction, but you might end up in a place like right here that is neither flammable nor water soluble, right? So there is a little bit of that as well, where it's like this latent space is very difficult to interpret, and even though you can literally type in whatever you want into this text, it's not like this is going to actually, there's no guarantee that this is going to be what you want, right? There's no guarantee that this is going to have high permeability or have water solubility or whatever you exactly want, right? And that's kind of what they're saying here, right? Like, for example, the hit ratio here for insoluble in water and hydrogen bond donors is like 20%. So you can say, I want this molecule, but make it insoluble in water and have hydrogen bond donors, and for some reason that's basically almost impossible. It's like you almost never end up with something that edited in the correct direction. And that is one of the negatives that they put in their discussion here, right? So in their discussion, challenges regarding evaluation. For the text-guided protein design task, the textual description is quite flexible, but the output proteins can be tested. Although most protein properties can be tested experimentally, the cost and the throughput can vary considerably. Generative models in art, language, and vision are often subjective and can be evaluated by a human reviewer. In contrast, protein engineering is objective but requires wet lab testing for most rigorous model assessment, right? So that's kind of the problem with this, is that when you're doing generative image stuff, right, you can directly test it out, right? So you can say, okay, here's a latent representing Shrek, and then here's a latent representing cats, and the latent halfway in between, I'm going to generate an image from that, and then I'm going to get Shrek with cats, right? And I can look at that and determine myself, is that Shrek with cats? Does that actually look like Shrek? Versus whenever you're doing this protein, generative protein stuff or generative molecule stuff, you can't really do that, right? It's like you can't subjectively evaluate this, right? Like, I don't know what the fuck this is, right? I don't even know how to make this. I don't know how to let alone evaluate that, right? So kind of one of the problems with the entire domain of biology and chemistry is that you can't like interpret what you're generating. If you actually want to be able to do that, you would actually have to like do wet lab testing, which means actually someone is actually like going and pipetting stuff into little beakers and then using that to actually do things and then testing it, right? So they do say that there are the validity surrogate oracles. So here, surrogate oracles, what that is basically a model that you give it a compound like this, and it'll tell you what it does. And I think DeepMind has a model like this, right? They call this synthetic or simulated biology, I think is the word that they use. But basically, it's like a model that tries to remove the need for a wet lab, right? So rather than having to actually make this protein or make this molecule and then test it, you can create these models that try to say, okay, what properties is this molecule going to have? But the problem is that these surrogate models are not guaranteed, right? So they're not. You actually need to do it in order to see it. You can't just hope that your surrogate oracle tells you, right? Because it could be the case that you feed this into your surrogate oracle and you ask it, does this have high permeability? And it says, yeah, it has high permeability. But then you actually go into a wet lab, you make this molecule, you test the permeability of it, and it's not high, right? Yeah, these tools still do not provide biological ground truth.
And until we have like a very powerful, perfect simulation kind of engine, we're not going to be able to get around this fact that we need biological ground truth to verify generative biology or generative chemistry, right? Which is not the case in my world of images and art, because you could evaluate it directly, right? There's no such thing as ground truth image space. You can evaluate that as a human and say, yeah, this is a good image, this is a bad image. But biological ground truth is like way more difficult to determine. Okay. Let me see. You actually evaluated on your question. Let me see. After you train CLIP, give an input sequence of chemical, how to generate description. You need a similarity matching, but how can we give a list of description text to compare the sequence? Okay, so you're saying, how do you get the actual text given the vector, right? So here, I think this is probably the easiest way to think about this. So this is the original CLIP paper, right? And in the CLIP paper, you have your text encoder, right? Your text encoder encodes this text into a vector, and your image encoder encodes this image into a vector. In this case, it's a sequence of tokens, right? But here you have a text, a piece of text that says a photo of a blank, right? And there's a blank there, right? Whenever you feed your image in here, you're going to be able to basically decode this the same way that a transformer model encodes your prompt and then auto-regressively decodes token by token, right? You can then say, okay, well, I want you to decode this last token right there, a photo of a blank, right? And what your decoder is doing is it's doing a classification problem effectively over all the different possible tokens that this could be, right? So there's 30,000 different tokens that are generally used in language, and when your transformer is decoding, right, it's basically doing a classification problem of 30,000 possible categories, of which is 30,000 possible tokens at every single token. So whenever you're decoding text, it's just basically creating that text one token at a time, solving this classification problem one token at a time, right? So in our case, right, we would feed it this molecule and it would start decoding, right, based on that, and it would start decoding autoregressively. So I think they actually have a picture of this. Maybe here in the protein one? Yeah, right here. Right, so here, output protein sequence. This is in text, but you can see here how this is an autoregressive transformer. You see you're feeding in your condition, which could be your vector, right? It's producing the first letter, then the first letter gets fed in, gets used to produce the second letter. So if you imagine this molecule has, and then you would be feeding in this molecule has with the latent vector, and then it would produce the next one, right? And the next word, high, would be basically picked from a set of all possible tokens that it could be using. Does that kind of explain Sikun? Okay. Hopefully that helps it, Sikun. Where it's like, maybe Sikun, what you're confused about is that open vocabulary decoding is basically like classification over and over and over and over again, right? So it's not like we're taking a molecule and then saying, okay, it has to be, here's like a list of all the possible texts, and then it basically classifies and picks one of these texts, right? Whenever you're in language space like that, what it's doing is it's running a classification basically every single token. So it's picking what every single token is. So that's why it can produce any text, right? Or it can consume any text. It's because it's basically, there's no, you can create any sequence of outputs there, token by token by token by token by token. Okay, hopefully that helped. GamerBG, bro, I need you to review Quip, the new state-of-the-art 2-bit quantization model. I would say you should check out our stream yesterday. We reviewed a 1-bit quantization model. So why quantize with 2 bits when you can quantize with 1 bit? Okay, I mean, I think we're pretty much close to done here. There's not much else to look at. Yeah, we talked about contrastive learning. This is basically the protein facilitator, little multi-layer perceptron. This is like the same basically pattern where they're using this guy didn't want to train these encoders from scratch, so basically these are pre-trained, and then he trains these little projectors, which are all little MLPs, which again is not even super powerful either. Little multi-layer perceptron. The diffusion model is a little bit weird as well. So the way that the diffusion model works is it starts with a noisy sequence. So most of you are familiar with diffusion models that work in the latent space of an image encoder, which is like this two-dimensional space, and it's usually a UNet. But you can also have a diffusion model that works in a one-dimensional sequence space. And what ends up happening there is basically you have the entire sequence, but then there's like masks, and then you basically predict these masks. The output predicts the masked amino acids at time step t equals 1. So basically this is what the diffusion model looks like. You start with random noise, and then you're basically predicting, filling in the random masked out tokens with the amino acids that you want, and then obviously the more of those amino acids that you have, the more obvious it becomes for this transformer to then fill in the rest of them. Sample the mask positions with probability 1 over t and predict the mask tokens following the distribution. So this is how the diffusion model for the protein is. Protein diff. They use an RNN and then a transformer. So this was the UNet, basically. The UNet in the stable diffusion here, instead of that UNet, which is a convnet because it's a two-dimensional latent representing the image. In this case, it's a one-dimensional noise sequence. So you use a recurrent neural network in a transformer. Emily wants the GitHub. Okay, I do have that pulled up. So this is the GitHub for the MoleculeSTM. 138 stars, not a huge amount of stars, but it's also kind of a niche concept, and it's also relatively recent. Pretty much entirely written in Python, and also written entirely by this Shengchao Liu guy. Here's the thing. Seems relatively simple. I haven't actually tried this out, but uses Anaconda for Python management. You got requests, matplotlibs, kind of standard stuff here. Bodo 3, this is S3 store. That's Amazon. Megatron. It's another popular little framework there. Actually, they never mentioned what they used to train this on, but here's your Hugging Face. I think if you want to use this, really the only thing that matters is this. Just use basically MoleculeSTM as a clip model, or use the protein clap, right? The next step for this type of research would be to basically use the full data sets. So obviously using the full data sets would work, or would be the next step that would produce a state-of-the-art thing. Also using better encoders that don't use BERT. That would probably be a next step as well. But both of those things are not things that you're going to be able to do as an individual researcher, right? So pre-training encoders, that's a lot of A100s, right? Cleaning up the UniProt data set to make an even bigger version of SwissProt clap, that's also something that requires a lot of time and money. So kind of all the things that are required to take this research to the next level, unfortunately require a lot of time and money. But that's probably not what you should focus on. If you want to take this kind of research and then do something cool with it, don't think about how to make this research better. Think about how to use these two models, how to use SwissProt clap, and then how to use the MoleculeSTM. Just think about, maybe even go to computer vision and look at how people used the clip model to do all kinds of cool things like stable diffusion, like a bunch of other random things like that. Try to use that as an inspiration to be like, okay, well, what can I do with SwissProt clap
and then MoleculeSTM, make that, and then after you're done doing that, you just wait a year, and then in 1 year, this guy here, Sheng Chao, he's probably going to get paid by NVIDIA again, right? Because this guy did it as part of an internship at NVIDIA. I guarantee you, NVIDIA is probably already working on bigger versions of these data sets, and then they're going to spend all that money to basically make the next version of these clip type models, and then you can just use those, right? So it's kind of like everything else now in machine learning and AI, where it's like, don't try to make better foundation models. That's like not your problem, right? As a researcher, making better foundation models is kind of a waste of time because you don't have the time, you don't have the money, you're not going to be able to compete in that world. Instead, think about, how do I apply this foundation model to do something cool and interesting and new, and then I'll do that cool, interesting new thing, and then once a better foundation model comes in, all I got to do is just plug in that better foundation model, and my cool, new, interesting thing will work even better. So that would be kind of my... See someone else interact with it. Yeah, I'm sorry, Emily. I didn't do anything with it. I also have an excuse. When I used to do these coding streams, I would basically be... I would be doing it on my Linux computer, and I would be piping it into my Windows computer, and then I would be piping my Windows computer into a server box that then multi-streams, and it was just a very complicated setup. So now I basically just only do the papers, because this is a Windows computer, so I don't even have my code set up in this computer. But that's kind of also why I stopped doing coding streams. It's just because it was like really annoying to have this like setup where I was like had like 4 different pipes going, and it was just like really, really slow. So now I just talk about the papers. Sorry if that's disappointing. All right, we got 10 minutes left here, so why don't we summarize what we did? If you guys have any questions, feel free to ask them now. I'm going to sip this coffee, drink some water, and then we will summarize this stream. All right, so Sukun asking the question, when we train clip, the vision encoder and the text encoder is pre-trained or from scratch? They're from scratch. So the clip image encoder and the clip text encoder are trained from scratch, and you can use them. So like clip, here you go. This is probably the most powerful, most popular image encoder. So this is the clip image encoder. It's a vision transformer, and it's based on this contrastive training. So in this case, they did train the image encoder from scratch, but they could have done the same thing, right? They could have taken a VGG 16 pre-trained on ImageNet, frozen that, and then trained a little projector on top of that, except the resulting pipeline would have been worse than if you just trained an encoder from scratch. The same thing happens here, right? Once they have the bigger data set, they should definitely train these encoders from scratch. And if they're going to train these encoders from scratch, they no longer need to use BERT as the architecture. So the next step of this would be to basically get rid of this projector, just make one encoder that goes directly from here to here, train it from scratch on the biggest possible data set. But as I was saying kind of before, that's not really something that you're going to be able to do at home, right? You're just going to have to wait for NVIDIA to give this guy money to do that. But once he does that, then that encoder is going to be the best possible encoder that you could have for this type of shit. Except that right now you're using this like weird frozen pre-trained encoder that was trained on some other shitty legacy data and uses a shitty architecture like BERT, and then this has this little extra projector here, which is a little multi-layer perceptron. Okay. Let's summarize this stream. So in today's stream, we delved into the biology and chemistry space to look at 2 new state-of-the-art papers, MoleculeSTM and ProteinDT. These are 2 papers that came out recently, 29 January 2024, and then this one's a little bit older, 3rd December 2023. These are papers produced by basically this same guy, Sheng Chao Liu, and then for some reason a huge amount of other institutions. It might be the case that these are just the people that provide the data, right? So there's like the people who do all the data and then the guy who actually does all the work. But basically what this guy did is he trained a clip model for molecules and then a clip model for proteins. So what a clip model does is it uses contrastive learning to learn a latent space in which you can compare images and text, or in this case, chemical compounds and text and proteins and text, right? So a latent space is something that looks like this, right? It's basically a space where you have little embeddings that live in this space, right? There's little vectors. Each of these points represents a vector of numbers, right? And the way that this space is kind of organized, things that are similar are close together, and things that are different are far apart. So what do you want to be close together, and what do you want to be far apart? Well, you want descriptions of molecules to be close to the encoding of the actual molecule, and you want descriptions of different molecules to be far apart from the molecules that are not them, right? So you want dissimilar or negative examples to be far apart, and then you want similar examples to be close together, right? And contrastive learning, which you can learn about here in Lil Logs, basically uses categorical cross-entropy loss, which is your standard kind of classification situation, and it's basically pulling together things that are similar, such as these two images of the dog, pushing apart things that are dissimilar, such as these images of planes and cats and the dog. In this case, they're doing it with descriptions and the structures. So the descriptions come from these two giant databases. So the database UniProt for proteins, and then the database PubChem for chemical stuff. These databases, they not just have the actual molecule and then the structure of the molecule, but they also have these descriptions. So basically, this is the text, and then the structure is a little string. But for example, in clip, this is the text, Pepper the Aussie pup, and then the image is the structure. But in here, this is the text, and then the structure is this. So the structure, there's a couple different ways of representing the structure of a molecule and the structure of a protein. But because ultimately you're going to be encoding this structure using, in this case, a transformer, you can't encode this is like an image, right? So you want to be able to encode something with a transformer. In order to feed it into a transformer, you need to turn it into a one-dimensional sequence. So for a molecule, you use what is known as smiles, which is basically this. This is like a string of letters which represent the molecule itself. And for a protein, you basically represent it as this, which is basically a string of letters which each represent an amino acid. So here, when they show you this little structure here and they're encoding it with ProBERT, or protein BERT, that's what they're using. They're basically using this like sequence of crap here. They feed it into a pre-trained transformer, and then out comes this little vector, which represents some point on some embedding space like this, some latent space, and then they're pulling together the things that are same and pushing apart the things that are different. Okay, so both of these papers are using data sets which are bigger than the previous state-of-the-art. So in this one, they're using SwissProtClap, which is a subset of UniProt, which is that database that we looked at. And even though it's relatively small compared to the data sets that people use for images, right? So in CLIP, people used a 400 million text image pair data set. That's multiple orders of magnitude larger than this 400K pair data set, which is SwissProtClap. But it's already like, I forget, it's somewhere on here, but it's like 28 times bigger than the previous data set that was used, which is why both of these are state-of-the-art, is because they're literally using bigger data sets than previous papers used. So that's how they were able to get state-of-the-art. But it's not going to be state-of-the-art for very long. One, because they're going to be doing bigger data sets, as we said, but then also because the encoders that they're even using, some of the stuff that they're using here is a little bit outdated, right? So in this case, whenever they're doing this encoding of the molecule structure and the encoding of the text, they're using a pre-trained BERT model. And they're using a pre-trained model here for the molecule as well, right? So they use this pre-trained BERT model called SciBERT, and then they use this pre-trained BERT model for the smile string called MegaMoleBART.
And then in the biology paper, kind of a similar situation. They're using a pre-trained ProtBERT, and then they're using a pre-trained SciBERT, so the same actual text encoder for both of these. They do that because they don't want to train these things from scratch because it would just take more time, more energy. So instead, they freeze these encoders, and then they train these little multi-layer perceptron projectors, and that's what they're actually pushing gradients into with this contrastive learning. So I think they could improve that. They could use something more modern than a BERT. But that's why this isn't going to be state-of-the-art for very long. It's probably going to be state-of-the-art until sometime in the middle of this year, and then they'll make better ones. But okay, now you have basically a clip model for molecules and a clip model for proteins. And what does that mean that you can do with this? Well, now you can do all kinds of awesome shit with this. You can basically do text to structure retrieval. You can do structure to text retrieval, which basically means that you can use text to search a database of structures, or you can use a structure to search a database of text. So because you can convert this into a little embedding vector, and you can convert all of these into embedding vectors, you can just use a cosine similarity to say, okay, well, which of these descriptions best matches this molecule? And you can say, okay, well, here's some new molecule that I found on this ant in the Amazon. Give me the most similar text descriptions or the embedding vectors for text that are most similar to that, and then there you go, boom. Here's a bunch of descriptions that are close to that. And you can also do just pure generative type stuff. So here they call it text-based molecule editing, but in the protein paper, they literally just go straight to text-guided protein design. And in both of those cases, what are you doing? Well, you're effectively doing exactly what image or stable diffusion does with image generation, right? Where you're using text to basically guide the creation via a diffusion model of an image. Except in this case, you're guiding the creation also via a diffusion model, except this is a one-dimensional sequence diffusion model based on a transformer, but you're generating a protein based on a text description. And in this case, it's also a little bit more complicated because they're doing this in the latent space, but they're effectively generating or editing an existing molecule with text. So this is pretty powerful because it means that you will be able to describe in natural language, I want a molecule that is water soluble and that produces this particular thing and also does this particular thing and then also contains these particular things, and you're just kind of like rattling this giant text description, and out comes this molecule. So powerful stuff. You know, I think this is the beginning, much like I keep saying this over and over again, and I'm sorry I keep repeating myself, but it's like much like CLIP was really the beginning of this entire explosion of computer vision research that used CLIP to do stable diffusion. We see it now everywhere in 3D generative 3D stuff as well. So any kind of like generative 3D Gaussians or NeRFs, they also use CLIP all the time. In vision language models, they use the CLIP image encoder, right? So like CLIP pretty much everywhere in the computer vision world. The same thing is going to happen with this, right? Where these two state-of-the-art, effectively CLIP models, but for proteins and molecules, you're going to see them everywhere, right? You're going to see MoleculeSTM and SwissProtClap. People are going to come up with all kinds of cool ways to do that. I think you're probably going to see these kind of like text database lookup things where you can just type in, I want blah, 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 and you just type in a little paragraph, and then boop, here's a protein. Boop, here's a molecule. Here's 10 molecules. So I don't know. That's all I got, guys. I'm kind of rattling off. Hopefully you guys got something from that. If not, I'm sorry. You know, I'm not a biology expert, but, you know, I know enough machine learning to kind of see this, and enough machine learning to be excited about this, because I feel like this is exactly what biology and chemistry needed. We needed these CLIP models, which are basically the beginnings of a bunch of cool research. And that's all I got. I'm tired. I've been ranting for 2 hours, guys. I appreciate all the comments. Thank you, Amelie, for recommending these and for kind of answering some of our questions. If you guys want to ask Amelie more questions, feel free to drop into our Discord. Thanks, Sukun, GamerBG, VR Wizard, Ed, 87GN, Aries, Majetti, Nuno. Thanks, everybody, for attending. Thanks, Wool Pumbaa. This latent space visualization, pretty cool. If you want any of these links here in the stream docs, this is a GitHub repo that I have.
You can look up the date of this particular stream, which is also part of the YouTube description. The YouTube description should contain this link. And you can go down here, and I have all the links for the different tabs that I opened up. So this is the ESM2 Genomic Atlas. So you come over here and you click Explore, and then that's the atlas. But again, this is not the actual latent space. This is a two-dimensional visualization of the latent space, right? In reality, these latent spaces are much more high-dimensional. So even though here you're like, oh, wow, look at this. This is like these two things are separated here, but that means that they're more similar to that. That's not the case, right? And like one example to showcase that is that, think about it this way, right? So this camera image is creating a two-dimensional representation of a three-dimensional space, which is me, right? So in that two-dimensional representation, right, here's two fingers that are a little bit apart, but if I go like this, right, the distance between these two fingers in 3D space is the same, but now I go like this, and now look at that. Even though the distance between these two fingers is the same in 3D space, in your two-dimensional projection of this three-dimensional space, they look way closer together, right? So if you were looking at a two-dimensional projection of a 3D space, you would say, hey, those two fingers are actually very similar, when in reality, they're much more separated. It's just that it's difficult to see in the two-dimensional representation or two-dimensional projection of the three-dimensional space. So the same thing is happening here, right? Where in this two-dimensional projection, it might seem that this and this are close together, and you're like, oh, wow, look at that. These two things are actually very similar. But it could be the case that once you actually go to a 128-dimensional space, this thing here is actually closer to this thing here than to this thing here. So that's just a little bit of a warning. Anytime you see these TSNE or PCA dimensional reductions of latent spaces, there's a little bit of fuzziness here, right? Don't read too much into it, but these are always really cool to kind of zoom in and click around and be like, oh, wow, look at that. All right. That's all I got. I already said thanks. You guys have fun, and see you guys later.